Hello, everyone, and welcome to this webinar on accelerating hybrid quantum classical computations. My name is Yuval Boger. I'm Chief Commercial Officer of Quera, the leader in neutral atom quantum computing. And I have several of my friends here today. Bob Sorensen from Hyperion Research. Hey, Bob, how are you doing today?
How's it going, Yuval?
Living the dream.
Yeah.
Arthur Strauss from Quantum Machines. Hey, Arthur.
How is it going?
And Ramon, also from Quantum Machine, who sort of snuck into the webinar without the slide.
Hi, how are you doing?
So we're going to give you various different perspectives on HPC quantum classical integration. I'll try to go first, give you a little bit of overview about Quera and what we do and how we play in this space. Then Bob from Hyperion Research will give, I'm sure, some interesting data on trends that he's seeing in the market. And then my friends from Quantum Machines will go last in this order. I want to encourage everyone on this webinar to submit any questions whenever you want. Just use the Q&A area or the chat area if you prefer. And I'll try to ask either answer or ask the other panelists as many questions as we can during this time. Whatever we can't get to, we'll try to do offline. So why don't we get started? So Quera, just a little bit about a company. We're located in Boston, close to Harvard and MIT, and we actually think that the fact that we are a bike's ride from Harvard and MIT is a strategic advantage that we have. We build quantum computers with neutral atoms. Many consider neutral atoms to be the most promising modality, the most promising approach to get to large-scale fault-tolerant machines. There's been so much progress in neutral atoms over the last few years, and I think it's fair to say that it went sort of from being the dark horse of quantum computing to being the workhorse of quantum computing. Quera's first machine, Aquila, 256 qubits, is available for anyone to use on Amazon since November of 22, and until just very recently, it was the only publicly accessible neutral atom machine for 2.5 years, and we're very proud of that machine, of course, but we're very happy with all the work that was done by hundreds of customers and dozens of organizations worldwide using this machine. We are fortunate to receive a $230 million investment in recent months, led by Google and SoftBank. And we partner with HPC centers and a couple of other organizations in the journey to solve classically intractable problems. We'd like to start from the customer. What do customers want? And we see three types of customers when we go to the market. The first is enterprise customers that believe that they could potentially leverage quantum computing to gain competitive advantage, to do things that their competitors cannot do. We see HPC centers that want to leverage quantum computers to solve problems for their customers, problems that classical computers cannot handle. And we see governments who are a major investor these days in quantum computing that seek to essentially generate economic prosperity. They seek to build a technology hub that attracts talent, research, and industry. And what's interesting about all of these is that they think about quantum computing not as the goal, but rather as the tool. Yeah, we can use quantum computing to get to where we want, as opposed to we want to do quantum computing for quantum computing's sake. Well, where are we in the quantum computing journey? At least that's my personal view. We're sometimes so deep in the trenches of the day to day that we forget to look at the big picture. And the big picture is that just a few years ago, certainly 10 years ago, but maybe even less, the big question is, could quantum computers be actually built? I mean, can you put together a computer with 2 qubits that does anything useful? And of course, many companies have answered that in the affirmative, and there are dozens of quantum computers with many different ways of conducting them. The second question was about error correction. Could qubits, the fundamental building block of quantum computers, are fragile. They're susceptible to the environment, whether it's vibration or heat or cosmic rays or electromagnetic interference or what have you. And unless you can detect and correct errors with qubits, then you're limited in the length of the calculation that you can run. And if you can't run a lengthy calculation, then quantum computers might remain as a toy, as an experiment, rather than a useful tool. And so the big question was, could errors be detected and corrected? And I think one sort of watershed moment in the industry was in December 23, where a paper led by Harvard, Quera, MIT, NIST, and University of Maryland showed a circuit with 48 logical qubits. Logical qubits are these things that groups of physical qubits that can detect and correct errors. And since then, other companies have also had really nice results. Google Willow is one of them that showed that, yes, error correction can actually work. So now we're at this stage where we say, can we make computers that are large and powerful enough to be truly useful, to go beyond scientists and say, can they deliver business advantage? And based on the progress in 24 and also this year, I think many organizations are starting to believe that truly useful quantum computers are just 2 or 3 years away. So we're no longer in the come back in 10 years. Now it's 2 or 3 years away. So I think many companies are saying, how about I just call you again in 2 or 3 years? However, we think that's not the right approach. I mean, I sometimes go to friends or to customers and say, look, you're not a medical doctor, are you? And if you had to pass a medical exam tomorrow morning, meaning a certification to be an MD, would you pass it, even if you could cram all night? And in most cases, the answer is no. But if you had to do it, and if it was really important to you and you had to do it in 2 or 3 years, I could probably come up with a program that does that. So that's where we are in quantum. I think we see more and more people that are starting today. They understand that the risk of waiting is much greater than the cost of preparing. During this time, we see people that are identifying the problems that would benefit from quantum computing, build the right team, develop some algorithms, simulate, test them against classical, and then identify the right partners, hardware, software, and cloud partners that could help in the journey. So speaking of the journey, we believe at Quera that we could be your preferred quantum innovation partner. And we do that with 3 pillars to our offering. The first one is quantum systems. We can deliver systems that are either on cloud or on premises. We do have a unique breakthrough architecture using neutral atoms. And with these systems, we can provide installation, support, community development, application development. So really everything you need so we can partner with you to reach your goals. We also do collaborative research. We work with universities and other research institutions on quantum error correction, on developing hybrid algorithms. And then we do application code design. In the current state of quantum computers, we believe that the full stack design of an algorithm is the right thing to do. And so we work typically over 12, 18 months with customers to identify the problem, to find the right algorithm, to simulate, to code it, to run it on the hardware, and to optimize. We build computers that are built for HPC centers. This is what you see here in the picture is a computer that we installed in the last couple of months in Japan at the institution called AIST, the National Institute of Standards Technology in Japan. It's right next to a 2000 GPU NVIDIA machine called ABC-IQ. So IST has invested in both top-of-the-line quantum computer from Quera as well as top-of-the-line classical supercomputer. We found that this computer, and I think the customer found that the computer is easy to install, no cryogenic cooling or very special requirements, requires less than 0.02 megawatts of power. I mean, I know that my HPC friends speak in megawatts. It is 20 kilowatts or less in power. And again, we have a team there that makes sure that the computer can continue running at top performance. And we work to integrate with classical infrastructure at various levels. So we think such a solution is really ideal for HPC centers that are forward-looking, that prepare for the quantum revolution. This is a photo from GTC, the big NVIDIA conference a few weeks ago. And what you see here is Jensen shaking hands with Professor Misha Lukin, scientific co-founder of Quera. GTC was a really important event for quantum. One of the interesting things is that NVIDIA announced the formation of what they call the NVAQC, the Accelerated Quantum Center in Boston, right next to Quera. We hope that's not a coincidence. Where Quera is a founding collaborator, and we're collaborating with NVIDIA on GPU and quantum integration, on trying to build some people call it the quantum accelerated supercomputer. Sometimes people call it just a quantum supercomputer. But the point is that we really work with the leader in GPUs to try and build the best of both worlds. And we also invite strategic customers to work with both companies to reach their goals. Supercomputers are used for many things. They're used for machine learning. They're used for weather forecasting. So I just want to give you a quick taste of things that quantum computers can be used for, and specifically Quera's quantum computer. We did some fascinating work together with Merck and Amgen and Deloitte on clinical trials. The issue with clinical trials, sometimes you have lots and lots of data. I mean, if you were testing the COVID vaccine, you've got millions of patients. But sometimes diseases are rare or treatments are expensive, and so the data set is very small. And with Merck and Amgen and Deloitte, and together with our help, we're able to show that a quantum machine learning algorithm outperforms, does better than any classical machine learning algorithm that they tried when the data set is small. So when the data set is small, again, we don't have a lot of patients, you can actually get more insights, better insights, faster insights using quantum computers. We also see supercomputers, classical supercomputers used in weather forecasting, and we did some nice work with Moody's. Moody's customers are insurance companies, and insurance companies really care about the weather and how that impacts their customers. So we work with them to create a model to predict the severity of weather events. But back to classical and quantum integration, this is how a typical deployment would look like. We would have an on-premises Quera computer. It would be next to a classical cluster, NVIDIA GPUs or classical CPUs. And then we'd have a whole suite of management layers, simulation, development tools, app store, training, and so on. Sometimes access is limited just to internal users. Sometimes access is open. That depends on our customer, to the global community or to their partners outside the organization. And then integration happens on two planes, on the control plane and the data plane. On the control plane, when we integrate quantum and classical, we have to think about job scheduling, whether it's Slurm or PBS or other devices or other systems. We have to think about user and identity management. HPC centers don't want to change everything when they integrate a quantum computer. They still want to have a billing system to identify who's using what. They want to be able to orchestrate these hybrid jobs. A lot of jobs today are hybrid, meaning certain portion is done on the quantum computer, certain portion is done on the classical computer, sometimes back and forth. So this orchestration becomes important. And on the data plane, pre and post processing of data, making sure the QPU executes, and then error correction. And one last thing I want to mention about error correction is work that we've published together with NVIDIA. And I think Quantum Machines will touch on that topic also in their presentation, where NVIDIA at Quera developed an AI decoder. Basically, the way quantum error correction works is that you measure the value of some qubits, and then you use that to determine if an error occurred and how to fix it. And you could do that through a sort of a complex algorithm, but it turns out that you could also train an AI model to do that with very, very promising results, both in terms of quality of output as well as speed. Last thing I want to mention is that we don't do it alone. We are really, really good at making neutral atom quantum computers, but we're not good at everything. And so we brought in a whole bunch of partners, including Quantum Machines, to go to us with customers and say, we bring a fantastic ecosystem. We call it the Quera Quantum Alliance. And we, again, help customers in this journey as we look at ourselves and hope customers look at us as well as their quantum innovation partner. So with that, Bob, I'll hand it over to you. And while I do that, let me see if there are any questions that I could answer. Please go ahead, Bob, and
All right,
I'll
great.
ask some of the questions later.
Okay, great. Thank you very much. I appreciate the invitation today. As you've all said, I'm Bob Sorensen, Chief Analyst for Quantum Computing at Hyperion Research, and we are not a quantum computing analyst company. We are an HPC company that consults to a large number of HPC suppliers and end users. And the reason we got into quantum was about 7 or 8 years ago. A lot of our clients, both on the supply side and the end user side, started saying, we hear some interesting things about quantum and we need to know more about it. The HPC world has an insatiable demand for increased performance capabilities, and they are ready to reach out to just about any kind of new technology that can accelerate their most important workloads. So the interest in quantum has always been high in the HPC world, and they are more than eager to adopt any new technology that can bring solutions to them faster, more performant, and increasingly at lower levels of power. So that's really how we got into this, looking at quantum as not a standalone sector, something that exists outside the realm of the classical compute world, but is yet another tool in the toolbox to address some of the most vexing computational problems that the HPC world lives and dies by. And the key to this feature is the timing for quantum couldn't be better, because there are so many concerns right now in the classical HPC world about where performance gains are going to be coming next. And if you look at exascale class systems at 10 to the 18 floating point operation per second range, those machines are creeping above the last big three procurements by the US Department of Energy, $600 million a piece, 4 years in the making, 4 years lifetime. And they may be running up electric utility bills that could easily reach $250 million during its lifetime. So quantum has a perfect position at this particular point in time to offer some mitigating capabilities, increased performance, lower power levels, and basically being able to offload some of the work from these rather complicated, expensive, complex to program, difficult to build HPC. So the timing for quantum couldn't be better. Before I get into this, I want to just tell a quick story. I was moderating a panel on quantum systems in front of an audience of HPC users about 2 months ago, and Yuval was actually on that panel. And one of the things that HPC users are most confused about right now are all the claims that they hear about. Oh, I've got this many qubits, and look at my T1, T2 time. Look at my quantum volume. Look at how well I did on random circuit sampling. And all that really does from the end user perspective is create fear, uncertainty, and doubt. They're not in a position yet to really translate what that means to their impact on their particular workloads. And so we kind of asked the panel what benchmarks really matter and what do they do when they talk to a customer. We went down and we kind of moved things back and forth until we got to Yuval, and he said, it's simple. We walk in and say, what problems do you have and how can we solve them? And I thought that was really, if there was a theme to this kind of talk today that I'm going to give, it's what problems do you have and how can we solve them? That's really the best way to think about quantum. So this is a summary of the 5th annual Global Quantum Computing Market Survey that I did at the behest of the Quantum Economic Development Consortium, which is funded by the National Quantum Initiative here in the United States, that provides significant amount of R&D funding and coordination with the federal government across the U.S. And actually to some extent international quantum computing development community. And I will say what's interesting is right now there has been discussion on the next turn of the crank on the National Quantum Initiative. They're looking at the next 5 years out. The initial one is basically running out of steam and it's time to renew. And some of the data that I'll show here today was actually cited in testimony by the QEDC to really get the Hill to think about why this is important, what it really means, and some of the value that continued government support to this important technology and why it's really required. So I just want to go quickly through some of the numbers here. This is our basically, I know Yuval hates this chart, but I like it anyway. It's basically, as I said, this is our 5th year study, and you can see we started this in 2019, and I like to keep track of where we were when we were making our predictions. And really what we're seeing here is relative stability and predictability in the sector, which I think is a really good thing. It makes government policymakers happy. It makes investors happy. It makes end users happy because they realize they're They're involved in a sector that's stable and predictable and moving forward. It's not as risky in the aggregate as some people could be led to believe. And so really what we come up with right now is in 2024, we were just basically the sector topped about $1 billion in revenue. We're looking at about a 27% annual growth rate out to 2027, which brings us to about $2.2 billion. As again, what I see here is, in the early years, we were looking more or less at somewhat of a linear curve, but I think we're really starting to see exponential curves starting to dominate. So I think we're going to start to see some significant increases in how this sector has impact from a revenue perspective. And some of the things, I don't want to go into all of these things. And as you've all said, this deck will be available at the end. So I don't have to, I could just go over it quickly. There's some interesting factors that are changing the dynamics of the market right now that are going to really make next year's prediction perhaps even more complicated than we've ever had before. We're seeing a real interest in orders and installations for on-premise systems. Previously or heretofore, the sector has really derived most of its revenue and its visibility through cloud access models. And that was a wonderful low barrier to entry for organizations to test the waters, to really kick the tires on quantum without having to invest significant amount of CapEx or OpEx to procure a system. They could jump from vendor to vendor, explore different modalities, but organizations are starting to make some decisions. And really that's going to be a major driver. And just some quick examples here. D-Wave, their 2024 bookings was exceeded 23 million. That was a huge increase over their 2023 revenues due to a single system procurement by Davidson Technologies, which is located in Huntsville, Alabama. For those that knows what goes on at Huntsville, you can understand what D-Wave's up to. As you've all mentioned, Kuwera, they're a $42 million contract, significant portion of the overall market. We're going to see more of those on-prem installations. We do have to be reminded, though, that when a company, and I didn't want to pick on anybody in particular, Company A recently posted revenues of almost $11 million, but at the same time, they had a net loss of about $200 million. So the sector is still not self-sustaining in terms of revenue generation. It is still driven by venture capital investment, corporate venturing, and government research projects as well. It's in its nascent stage. This is to be expected for new technology, but it's why it's important for continued stability and progress, demonstrated progress in the sector to ensure that the funding continues to roll in. And we're starting to see that already. If you look at the bottom, venture capital startups, about 1.5 billion last year, 2024. That's up from 963 million in 2022. The issue here is, most companies are still private, and most intend to stay that way for the next few years. Again, not a revenue stable sector yet. Bob Suter, who's a colleague of mine, recently released some quick analysis that said right now there are 81 different quantum computing suppliers in the world right now, and that's a huge number. And there is going to be some fallout. There's going to be some winners and losers coming. The winners will float to the top. So churn is going to be available. It's going to be a necessity. The best are going to win, and there's going to be some issues falling by the wayside. But it doesn't really speak to the vitality of the overall quantum computing sector. So when a company goes south, don't think it portends the end of the world. It's really a natural progression of survival of the fittest. What's interesting is we talked about QC partnerships, and really what's happening in the sector right now is quantum computing suppliers are reaching out to end users, perhaps some such as the folks that are on the seminar today, and we're basically asked them why. We asked quantum computing suppliers, why are you partnering with end users? And here what we found is that about 71% of the organizations we talk to have a partnership with at least one quantum computing end user, and they're doing things that are pretty obvious. They're exploring vertical specific QC related opportunities. That goes back to Yuval's statement. What problems do we solve here? They're not interested in developing new technology or exploring different quantum modalities. They have problems they want to solve, and they want to do it within their particular workloads. So it's if I'm a pharmaceutical company, an aerospace company, an advanced manufacturing company, I have specific compute requirements and I want to know what quantum can bring to the table. And really the best way to do that at this point in time is to choose a partner in the QC world and really start to explore the unique capabilities that quantum brings to the table. And we'll get to this in a minute or two. Most importantly, how can you integrate that quantum computing capability into your overall existing classical HPC infrastructure? These are some of the end user motivations about why organizations are seeking quantum computing capability. Certainly implementing new algorithms not possible on classical counterparts, but almost equally important is concerns with future capabilities of performance increases in classical computing. As I said, it's becoming more expensive and complex. Can quantum fill that gap? They want to explore use cases, and I found this interesting. No expectation of near-term advantage. That 47% of the surveys, people, the organizations we surveyed, said they're not really looking at near-term advantage. They want to basically understand what's relevant from a use case perspective. Again, exploring potential here, as opposed to looking at return on investment and real hard and fast technical results. That brings us to that estimate that I think Yuval and I agree on, 2 to 3 years before we really start to see very demonstrable performance gains on quantum systems that outperform classical counterparts significantly. When we asked about greatest hurdles to adoption, and this is the big one, and we get this all the time with new technologies, how do you integrate a new technology into existing infrastructure? Another hurdle right now is lack of in-house expertise, which is why organizations like Quantum Machines can help bridge the gap in terms of integrating a quantum system with an existing classical counterpart. I always like to say, I looked at their QBridge capability, and as soon as an HPC user sees the word Slurm, scheduling, they're like, okay, I get it. This makes me happy. I have some capabilities here to integrate more effectively. And that's really to overcome some of these hurdles. It's all about integration, and it's all about the fact that you have to be able to bring that system into an existing infrastructure, address the applications that matter, and then have the subject matter expert or the researcher at hand hit the load and go button. This is just some quick stuff on major algorithms by revenue. ModSim, optimization, and AI continue to be the big three. We're seeing some sense of hybrid, the idea that ModSim and optimization can be merged together to do some interesting things. The big three, the holy trinity, if you will, ModSim, optimization, AI, have always been the main ones. And will continue to be as the technology moves forward, at least for the near term. Right now, cloud continues to dominate. When we asked about hardware revenue by access model, cloud is perceived to be in 2027 worth about 38% of the overall revenue base for access to hardware. But the on-prem sector, as I said, is really moving up now. We're starting to see that the change happening where on-prem is definitely the way to go. This is an interesting one where we asked the organizations about the architectures that they see right now, NISQ's architectures. This is questions for where do you see the world in 2027? NISQ will dominate, continued in 2027 at about twice the rate of universal error-corrected gate models. That may be a little bit optimistic, but what we saw this year was the rise of interest in digital simulators, both CPU and GPU-based, but GPUs are preferred at about 2x the rate of CPUs. I think that's a lot of that has to do with what you've all mentioned, the real interest in NVIDIA. Jensen announced that quantum wasn't going to be around for 15 years, and then somebody sent him an email that said, you need to reevaluate, and NVIDIA has jumped whole hog into GPU-based simulators for quantum, a real advantage to help accelerate the research and development of algorithms and applications and verification and validation of the quantum process on a system that is not, at this particular point in time, saddled with error concerns. This is the top end user sectors, and this is, of course, a standard eye chart, a little bit blurry. But the key here is when we asked organizations that supply quantum, what markets are the most promising end user sectors for 2027? And right now it's chemicals and chemistry, excluding pharmaceuticals. Then you have R&D into quantum technologies, pharmaceuticals, university, financial, government labs, cybersecurity, and such. The key here is the depth and breadth of interest that quantum within the realm of their application, specific kinds of advantage, jobs where they can really outshine classical counterparts. There are considered applications in almost every vertical that we track in the HPC environment, where some organizations said there's opportunity here for quantum. So while one could say, oh, quantum is good for a limited case of applications, it's not the answer to everything. The response to that is yes, but those applications have applicability in just about every major commercial, academic, and government vertical that we track. So that's a really good story in terms of the continued interest in the technology. We asked a kind of capricious question here about quantum computing distractions and large language models. A lot of money right now, a lot of interest is going into things like GPU-based large language models, the text-based kinds of AI that basically have consumed the enterprise world and to some extent in the HPC world. But really, I think what that does is so organizations within the quantum computing sector are saying that there may be some near-term distractions. But what I think is that this demonstrates the need for quantum to continue to deliver on its technology and performance gains, move on that track. So when large language models and the enthusiasm there starts to wane, which I think invariably it will, quantum can again emerge as the next big thing. But what it really shows is high user interest in performance gains. If the new bright shiny object comes along and has some potential for demonstrated performance gains, they're going to go after it big time. And if it works or if it doesn't work, that remains to be seen. But there is so much pent up demand right now in the HPC world for compute capability that can move them down the road on some of the most complex computational jobs. And quantum is positioning itself very well to move beyond this, and its schedule and its time frame and its rate of progress seems to be really on track. As I said, as Yuval and I agree on, about 2 to 3 years going forward. So that's really a quick and dirty of some of the work here. This is my email address. If you have additional questions, I have a much larger deck where when I have more than a few minutes to talk, I don't have to talk as fast, and I have more details going forward. But that's kind of a quick overview of the sector, and I think we're going to do we're going to move now to a little bit more of a deep dive into some of the more compelling technologies that we promised in this event.
Thank you very much, Bob. To use an ESPN analogy, that was the fastest 10 minutes on television. But let me ask you a couple questions that came from the audience, and please feel free to submit additional ones. So when people talk about classically intractable problems and that may be solved by quantum, what problems do they have in mind?
To me, the biggest one right now is computational chemistry. It's the idea that you could do some incredible modeling within the quantum realm that is beyond what you could do on a classical computer. If you look at how you say protein folding or trying to calculate the lowest energy state of a molecule, in the classical world, you have to make so many assumptions, simplifying assumptions to say, well, we'll ignore this because it adds too much compute capability. We'll ignore that. And the beauty of this is for those kinds of computations, you have the perfect quantum situation. You don't have a lot of data input. You have some initial conditions and some governing interaction equations. You toss that into the quantum realm, and all of these complex interactions take place naturally within a quantum computer. And then your end result is a very simple output. And that's really where quantum shines right now. It's simple input, simple output, and incredibly complicated interactions within the quantum realm. And so computational chemistry and modeling and simulation writ large are really great use cases. Optimization is another good one. I like optimization because it's near term. And the beauty of optimization is it doesn't have to be perfect. It only has to be better than what a classical counterpart can give you. So it's a much more error tolerant kind of application. So to me, optimization near term, computational modeling and simulation and all those sorts of things. That's why you saw interest in pharmaceuticals, oil and gas companies. They want to understand oil at the molecular level so they can start to build better models on how to extract it from underground and such. Lots of opportunity there, but the key is staying within the quantum realm to deal with quantum phenomena at the molecular level is a huge game changer for the sector.
1.5 additional questions. The first one is when you show the market size, an audience member asks, do these figures include peripherals and integration infrastructure? Can you comment on the potential scope and scale of the market for auxiliary subsystems?
This survey, and it was basically, we went out and surveyed quantum computing suppliers, and we asked them for their pure revenue. Now, we have a chart that shows how much of this was for hardware, how much of this was for software or professional services or middleware, but it was basically for the revenue of the quantum computing supplier. So if they're selling a complete system that has a classical control system and such, that would be wrapped up into this. But right now, because it's really cloud access models, most of the revenue we're seeing from these companies comes from a cloud interaction, more of a professional service relationship than the shipment of a finished product. And that's why we talked about a potential hockey stick. Once you start shipping finished systems, you're now selling a complete system with all of the classic control systems, if you have a file system, something else that needed to support that system going forward. But at this particular point in time, because we've only really seen a small number on-prem procurements. It doesn't really include all that outside classical kind of hardware.
And the half question is, as I look beyond your right shoulder, is that a quantum computer from Lego bricks?
I put that there. Very good eye. Very nicely done. Yes, it is.
Very good. And yes, those of you that are interested will be able to soon get your own model as well. So with that, we're having too much fun. So Ramon, why don't you take the next step?
Sure thing. So I let Arthur share the slides. So we'll take it up a notch in terms of technical discussions, and we're gonna shift basically from discussing what quantum can do for HPC users to what HPC can do for quantum builders. Basically, we need HPC infrastructure to make the quantum computer work in the first place. And so to do that, first we need to ask ourselves what are the requirements for kind of real-time compute and heavy classical compute for the realization of quantum computing at scale. And so you can read more details in these recent publications we did, where we really took Shor's algorithm, a small one, where we factorize a 5-bit number 21. So it came out to be 7 times 3, but we did that fully with fault tolerant qubits on surface code, all the way down, simulating everything all the way down to the pulse level, and trying to figure out what really are the requirements for different kind of qubit modalities, from the decoders, quantum error correction, classical logic that needs to run in the background. And so we've seen, the strictest requirements come from solid state qubits, not atoms. Atoms and ions can idle and wait for classical compute to get back from a decoder, or at least much more so than solid state qubits. But because we serve all qubit modalities, they kind of define the requirements. And so we have about 10-20 microseconds of round trip latency that we think will be necessary in order to extract noise fast enough from these solid state qubit systems. The details of how we get to this number, please read the paper. So for atom arrays and ions, these numbers would be much more relaxed, but there still remains this challenge of maintaining multiple parallel decoders that have to run and decode and extract noise from multiple surfaces, something that atom arrays have been demonstrating recently more so than solid state qubits. We have demonstrations with tens of logical qubits, right? So in a real fault tolerance or quantum error correction program, each one of these, or many of these, will need a classical compute kind of kernel that will follow them and remove all this noise. We still need, so the latency needs to be well below 10 microseconds round trip from the controller, from the FPGAs and the DUCs and the ADCs that drive and read out these qubits to an external computer, CPU, GPU, or application-specific ASICs based, where you would put the heavy quantum error correction logic, the decoders and logical circuit, and so on. And also on the control side, on the signal side, we still need very low latency interfaces that stays within kind of the signal processing processors, the FPGAs and so on, in order to remove classical noise that we know we have regardless of kind of quantum error correction, stabilizing laser intensities, different phase noise, and for that you need to measure something and respond in nanoseconds. We're trying to build an analog computer here, and that failed in the 70s because we could not remove noise. The operations were noisy, and at a certain program depth we got garbage. With quantum error correction, we can circumvent this and allow us to move forward, but we need large classical computers sitting side by side to our qubits to remove this noise. Next slide, please. And so to do that, we've partnered with NVIDIA to build a reference architecture, which we call DGX Quantum, which is a low latency PCI Express link between NVIDIA Grace Hopper servers and Quantum Machines controllers. So this is a PCI Express card that sits inside a Grace Hopper superchip server, and connects over fiber to our OPX controllers. And you can now share data, variables, waveforms, integration weights, and so on with under 4 microsecond round trip latency. Round trip means I send variables from the FPGA, from the controller to the GPU, say. The GPU adds them up and sends back the response. That's below 4 microseconds. So this is a latency that is low enough to allow to execute different kinds of decoders on CPUs and GPUs and write them from a high-level programming language like C++, CUDA, Python, or QA for the sequencing. So from something where the community can easily adopt and play around and study kind of the interface between signal synthesis and sequencing of pulses and classical computing outside. Next slide, please. So for atom arrays, which is kind of the host preferred qubit modality. So they have always demonstrated impressive scaling with very few control lines in general, but still there is inhomogeneity over these qubits, over these laser beams that drive these qubits, and temporal drifts that exists on all qubit modalities. And these atoms also move around, so they kind of couple spatial inhomogeneity to temporal fluctuations. And all of these noise, all of these temporal and spatial fluctuations need to be removed in order to maintain kind of the fidelity of the operations that we do below the quantum error correction threshold for the code. And so for that, we believe we need a lot of classical compute. To demonstrate maybe quickly one slide, although we don't have much time, maybe we skip the next slide. So this is just to show the kind of timescales that qubits can drift on. So this is a transmon, but we have similar things that we can show also for atoms, for laser intensity or phase fluctuations. This is the fidelity of a single qubit, and we see that it starts to drift on a 10 millisecond timescale, indicating that if you want to run a job that is an hour long, these signals, the amplitudes, the frequencies, the phases needs to be stabilized on timescales running anywhere from a few milliseconds to days. Atom array can run for very long. And so these things require on many channels. These are things that happen per qubit. These calibrations are scaled with the number of qubits, and these things will need a lot of classical compute in the background to kind of address. And so so we need a lot of classical compute to remove this noise, temporal and spatial. And Arthur will present in the few minutes that he has left kind of a framework to do that consistently. So thank you.
Thank you, Roman. So in the next few minutes, I will try to tell you about the story of how we actually, in practice, calibrate those quantum operations that Roman talked about. And so those span from gates, measurements as well. And first, I need to take a step back and tell you about like the story of how we usually do things in the lab. So the usual starting point when you want to prepare some operations that we will commonly call quantum gates in this setting is basically relying on the existence of a model. So you have a quantum system upon which you rely on a description. Usually it can be a Hamiltonian description or Weyl if you're dealing with open quantum systems. And on the classical computer side, or analytically speaking, you want to derive from this model and the knowledge of the unitary operations you want to create on your quantum computer. You want to find analytically and with numerical optimization methods the optimal pulse shapes that you should send to the quantum system to steer it towards a specific target state or a target unitary in the case of a gate calibration. So once you found those numerical parameters for your pulse shapes, this is where you would load things into your control stack, which would be composed back in the day of many different kind of devices, arbitrary waveform generators, lock-ins, digitizers, all those things, which eventually will be, you will be storing all those instructions over here to eventually play them in a kind of plug-and-play approach to the quantum system. And at this stage, it's, a pray for the best kind of scenario because the quality of the actual gate you're sending on your quantum system will be pretty much dependent on the quality of the model that you had in the beginning to describe it. And so clearly, as the movie says, like theory will only get you so far. And it is often the case that this stage in open loop optimization is not enough. So we need to resort to a second stage, which is usually complementary to the model-based approach, which is model-free approach. And by model-free, I mean that now you're relying solely on experimental data, so measurement outcomes that you will collect from the quantum system itself to modify iteratively the parameters of the gate set you try to optimize. And this is where the problem starts to come in, because if you think about like the communication pipeline that is usually involved, and especially in a setting like reinforcement learning, where you might want to try many parameters to explore the landscape, you really run quickly to compilation overhead. And as you can see in this figure that I drew from a paper doing error correction from the Yale's group back in 2023, the main idea was that the whole execution budget was mostly dominated by the compilation, mainly the time it took to synthesize the instructions, the waveforms, and upload them to the control system, and upload the quantum circuit or the program that was associated with it. And so what we want to aim to do with DGX Quantum is really suppress completely this runtime overhead. So I will try to show you the few strategies we came up with to really leverage to the best of the platform that we have today at Quantum Machines. All right, so the reinforcement learning framework that we chose, and I will try to explain why we went for this solution. The first requirement was that it was a model-free method. So the setting here is that we're relying solely on measurement data, as we pointed out in the model-free case before. And reinforcement learning is one of the three branches of machine learning, which essentially relies on an interaction between two entities. The first entity is what we call the agent, and which will typically be represented by a classical neural network sitting on the PC. In our case, it will be on the Grace Hopper server. And we're going to leverage the OPNIC and the low communication latency to stream what we call the actions. The actions are what the agent is able to send to the quantum system to try to steer it and intend to prepare a certain target state or to create a certain unitary. So what are the parameters that we're talking about? So typically, the parameters of the pulses we might want to focus on here are parameters that we can leverage in a very fast fashion thanks to our OPX 1000. In fact, the OPX 1000 carries what we call the hybrid processing unit. It's an FPGA-based processor, which enables us not only to do classical processing in real time, but also to modulate the pulse output in real time. And this offers a lot of flexibility because instead of having to recompile new waveforms every time you have to try out a new set of parameters, you can straightforwardly, from the baseline, modulate the pulse answer. And there are many parameters you can tweak: the amplitude, the duration, the frequency, the phase, and many others with some adjustments, and eventually you play those things and those knobs, and it enables the agent to explore in a much faster fashion the parameter space, and eventually you try to prepare the unitary that will correspond to the target you set your mind to. How do we train the agent? So we have to get some kind of cost function. In reinforcement learning, we usually coin this as a reward signal. And this will be based on a very well-known scheme for fidelity estimation, which is coined direct fidelity estimation, that came out in 2011. And essentially, the main idea of this protocol is to focus on the set of input states and observables that are the most relevant to compute for our specific target unitary. And so this enables us to bypass the need for doing a full tomography, and more importantly, to maintain a circuit structure which is essentially fully parametric. And we're going to leverage this fact to yield the best performance and lower, again, the compilation overhead. So this is the kind of quantum programs that we want to run with an OPX 1000. So in this particular case, when you want to compute a different observable every time, or a different input state preparation, which are represented by those two steps that you see over here, represented in green in this case, the main thing is that in the traditional scenario, each different input state and each different measurement that you want to carry on will consist in another circuit. And you can imagine that if you want to do things in parallel over hundreds of qubits, for instance, you will have to compile very different, many different variants of the same quantum circuit, although they actually carry the same structure, because what you are most interested in is really the central block, which is the channel, the gate that you're trying to essentially calibrate. So in this particular case, we are able to leverage what we call the switch statement. So we leverage the fact that the hybrid processing unit is able to carry control flow in real time. And in this case, we're going to just feed one variable. Usually, it will be 1 or 2 bits, for example, to stream from the DGX to the OPX, such that it can make the decision shot to shot which of the input states to prepare, and similarly which observables to measure. And so this simplifies dramatically the amount of communication we have to load, and again, we can really optimize the direct fidelity estimation scheme to a shot-to-shot basis. And this is what is really changing the scope over traditional calibrations. On the other hand, there is another fact that we're leveraging here, which is that the action, so the parameters describing the CZ gate used here as an example, are not full waveforms that are ready to be recompiled. Instead, those would be key parameters of the waveform that we can actually tweak without ever changing the program structure. So same thing, the DGX server is going to upload based on what the neural network tells us to do, what the parameters are doing, and essentially once we updated those parameters, the OPX can just modulate its sensor. All right, so I briefly wanted to sketch like those results that we have demonstrated a few weeks back at APS, where we prepared the GHZ states over 3 qubits, and we used exactly this direct fidelity estimation scheme. So in this case, we were not relying on randomized measurements. We actually computed all of the expectation values together, the ones that that you see here. And we used 6 parameters in total that were all tuned in real time within the OPX. So those parameters were part of the circuit that you see here. I won't go too much into the details, but this training kind of iteration shows you that the more the agent is able to learn, the more it is able to prepare the actual GHZ state, as confirmed by all the expectation values we were able to reconstruct. All right. So in the last few minutes that are remaining, I would like just to tell you about like how we can take an extra step by embedding machine learning even closer to the hardware, and why it's becoming more and more important. So in the case of reinforcement learning, it's a specifically interesting case, and that's why we chose this method. It's that the whole strategy is not to try to directly optimize over parameters. Actually, in reinforcement learning, what we're trying to optimize is what we call in the jargon a policy, namely a probability distribution that we usually represent as a multivariate Gaussian distribution in this case over the parameter space. And this choice is motivated by the fact that the agent wants to explore many different parameters with some uncertainty about which parameters are actually yielding a high reward. So typically, you can imagine that at the beginning, we will have a Gaussian distribution whose standard deviation will be extremely broad. This enables the agent to explore and resolve the parameter space quicker. And on the other side, the mean will be mostly sampled at random in the beginning. But as the training goes along and that the agent learns the correlations between the reward and the actions, the mean is going to slightly focus and shift towards the actual value we're looking for the parameter vector. And the sigma, the standard deviation, is going to shrink and reduce, therefore, the uncertainty about what is the optimal value we should aim. And now we're changing slightly the paradigm that we used before, where we were uploading all the actions that were therefore sampled from this policy on the DGX side. Here in this case, what we are uploading to the OPX 1000 is directly the parameters of the distribution. We also load for the direct fidelity estimation scheme the necessary inputs, so the observables and input state fiducials in this case. And now we're leveraging another key component of our HPU. The HPU is actually able to also do sampling in real time. We have a random number generator incorporated in the controller, and that enables us to actually parallelize the sampling of new actions. And so typically the B here that you see represented is a notion of the batch size, which is a typical notion in machine learning. We want to explore the larger the batch, the better the exploration will be, and therefore the agent will be able to resolve quicker the quality of the policy it chose at the beginning. And once we have sampled this action, we are ready to synthesize on the fly, again, with this real-time amplitude, real-time post level parameterization to fine-tune our quantum circuits of interest. Another key phenomenon is that usually when you have to do backpropagation, namely, then you have to update the network here, you usually have to stream those actions. The agent has to know which actions were sampled. So instead of having to stream back those actions, we actually come up with a strategy where the DGX samples asynchronously by being given the same seed as what is occurring on the OPX, the same action, so that we make sure that those pieces are completely independent, therefore limiting as much as possible the communication data flow. And as we will see for the next use case, it's actually very important to be as steady as possible on what data we are transferring. The rest of the algorithm is pretty straightforward. We keep maintaining exactly the same thing. We transmit on the quantum computer the tentative action that we set. We collect the expectation values of interest and stream them back to the agent once we're ready to process the reward and do a parameter update and try out iteratively until we converge. All right, I will briefly conclude with this outlook here. So here I showed you how, we could resolve a very fast calibration. Actually, the previous results I just showed you were computed in less than 30 seconds of workload time, which is really impressive. And the next iteration, where we embed even more the integration, will probably yield shorter timescales even. So the hope in this case is that we really want to embed as close as possible to what is coming up. And in the HPC era, when you're going to be interested in computing real applications, you will need error correction. And error correction requires lots of data coming. And we briefly mentioned it before. Decoding is an important part of the story. And so now what we envision as an extra level, and what we could do with DGX Quantum, is to embed the two abstraction layers altogether. So decoding normally is set only for detecting and correcting errors. But what if we could also influence the parameterizations of our gates in real time to lower the burden of decoder? So meaning that we lower dynamically the physical error rates that are evolving, and they will evolve based on the drift discussion that Ramon mentioned earlier. So this perspective opens really lots of exciting opportunities for people to play around different abstraction levels, to move towards full static circuits, to hybrid classical quantum programs. And this is really an exciting direction that Google undertook in a simulation project back in 2016, where they were indeed trying to fight the drift of a frequency parameter while collecting syndrome data from a repetition code experiment. All right, I will wrap it up. So in those 2 minutes that we had to show you what we're up to at QM, we showed you that we definitely require fast calibrations. And the more we advance and the more we scale, those will need to be even faster. So we need intra-job and intra-job sensitivity. And this is why we believe that reinforcement learning and this policy exploration is going to become critical in that aspect. On top of that, we have the ability to navigate between abstraction layers, which is also going to be important, because as you want to do some co-design approach, some high-level optimization, you will need to be able to know what it boils down to eventually on your quantum computer. And finally, I hope I convinced you that the unique structure of this hybrid processing unit is really moving us away from the static quantum circuit model of quantum computation. Instead, we're moving to something much more dynamic with additional features such as control flow, but also real-time random sampling, some adaptive settings that could be used in a variety of use cases. Think about error mitigation, error correction. The possibilities are really endless, and we can't wait for people to try out this brand new product for all those exciting aspirations. So we did.
Thank you very much, Arthur. This was really great. So what in this webinar, what we've seen is multiple aspects. One, I think we discussed that QPUs are really going to be an integral part of the future of HPCs. A couple of months ago, I wrote an article that says the QPU is the next GPU. And immediately I got a call from my friends at NVIDIA. So what do you mean the QPU is going to be the next GPU? We really like GPUs. No. The QPU is going to be the next best friend of the GPU. We also saw from Bob that a lot of HPC centers are looking at this. And from Quantum Machines that quantum and classical resources can work together. They can work together algorithmically. They can work together on the low level. There's AI for quantum, there's quantum for AI. And so I think both the classical and quantum parts are truly inseparable. If I can ask you in really 10 seconds to have your sort of last takeaway, Bob, perhaps?
You're muted. All right. The time to start is now. Preparation needs to be done. So when we hit that sweet spot in the next 2 to 3 years, where we could use Yuval's tortured metaphor of the med student, you really want to start looking at the workloads that you have specifically. Don't look for the end all be all algorithm that's going to solve everyone's problems. Look for the computational solution that quantum brings to your particular workload.
And Ramon, any last words from you in 10 seconds?
Yes, I think it's very exciting that we're approaching an era where we could test and try kind of at the tip of our fingers a quantum error correction fault tolerance operation with systems that are coming up and being available soon. So I think the future is bright.
Very good. Thank you, Ramon. Thank you, Arthur. Thank you, Bob. And thank you all the audience for participating here. And we look forward to seeing you as early as next week in our next webinar on error correction and on some of the exciting science with Quora. Thank you very much.
Thank you, Yuval.
Thank you.